All right. So I'm pretty sure in the first semester we mentioned what a solution was. In fact, a solution is a homogeneous mixture of substances. And remember, mixtures are combinations of materials, of substances, where each substance in the combination retains its own identity. That means they can be separated by physical means, filtration or distillation or some other physical process. So we don't have a chemical reaction in a homogeneous mixture, aka solution. Solutions, though, a popular misconception is solutions can only be one type, like a solid dissolved in a liquid or something dissolved in water. Everybody thinks that's a solution. Well, it is, but it's not the only solution. There are whole lots of other combinations that you make. Any of the phases, gas, liquid, solid, can be combined to make a solution or a homogeneous mixture. You can combine several gases and get air, like 78% nitrogen and 21% oxygen and about 1% argon with some minor components. And that's a solution of gases that we breathe every day. A lot of people have a strong attraction to alcoholic beverages. That's a solution of ethanol and water and some other things. Antifreeze is a solution of ethylene glycol and water. Put that in our radiators to keep them boiling over in the summer and freezing your engine into a solid block of ice in the winter. And that concept, we're going to attack that concept later in the lab. Here's one that people definitely don't think of as a solution, and that's a solid in a solid, like brass. Brass is mostly copper, but it has a significant amount of nickel in it. And but how do you get them mixed? If they're both solid, we have to melt them. Yeah, have to melt them together and make a solid solid. Do the same thing with steel, right? You have iron and carbon, two solids, and you make a homogeneous mixture of carbon and iron. Carbonated water is one where the gas is dissolved in the liquid. And we'll talk about that one again also. Now, here's what most people think of as a solution, as sugar water like you make for your hummingbird feeder, or salt water that you make for a sore throat gargle. Seawater is a solution of solids in a liquid. That seawater is about, is it 0.35 or 3.5? I think it's 3.5% dissolved solids. It's pretty high. Anyway, you can also have a solution of a gas in a solid, which seems kind of weird. But you'd probably drive around with one every day. The catalytic converter in your car is a ceramic matrix that's coated with platinum and palladium as a catalyst. And as the gases pass over that, they dissolve in that metal and react. And you get your unreacted carbon compounds, and your nitrogen oxides are converted into dinitrogen, so you don't get smog. But any of those possibilities will give you a solution, a homogeneous mixture. Now, we need a way of expressing the concentration. If a homogeneous mixture is a combination of substances that retain their identity, then they deserve an expression of how much there is in the solution, each one. If you only have one solute dissolved in a solvent, then you'll only have one expression of concentration. Solute is the minor component, and the solvent is the major component most of the time. When you first start making your solution, it'll be that way. You start off with water and you add salt to it. You get to a point where you're about 35 grams in 100 milliliters will dissolve sodium chloride, so it's very soluble. Sucrose, table sugar, is even more soluble. You can keep adding sucrose as the solute until you've got more solute in your solution than you do solvent. And that's an industrial advantage, because if you have a plant where you're processing foods usually, and you need to get sucrose from one side of the plant to the other, it's easier to get it there if it's in a liquid form than it is in a solid form, right? You have to use maybe a conveyor belt or a bucket chain to move solids. But if it's in a liquid, you can just pump it through pipes. And that's what a lot of companies do. They saturate to the maximum amount that sugar will dissolve in water, and then run it through their pumps, and they can send it anywhere they want. I got a little book like this. It's called "This Is Liquid Sugar." Talks about doing that with sugar. But you want to know what concentration you have. And there are several ways to express that. And 4 of those are given here. The top one, and we're going to go through them individually. All right, so there are separate slides for each one of these ways of expressing. Molarity is moles of solute per liter of solution. So that's a number of molecules dissolved in a certain volume of the final solution. Mass percent. Now, one thing about molarity is it's temperature sensitive, right? Because one of the parts of that calculation is volume. And if you change the volume of a liquid, it's going to change the concentration. The next one is mass percent, mass of the solute per mass of the solution, right? That would be insensitive to temperature change, because mass doesn't change with temperature. Mole fraction is sometimes useful, particularly when we're talking about gas solutions. That's moles of one of the solutes per total moles of the solution. I accuse your classmates of stuffing you in a trunk. I guess you found a way out.
I see.
Now all of that is you've had before.
Okay.
Okay. Those first 4 on the left are new for everybody.
Okay.
But we were not going to use those until the lab discussion. You can take a copy now if you want. Yeah, mole fraction. So we're just ratioing the number of moles of one of the solutes to the total moles of the solution. And the name tells you actually what it is. It is a fraction. It's always going to be less than 1, right? If the mole fraction is 1, what does that mean? That means that the solute and the solvent are identical. It's pure, right? If it's less than 1, then you have some solute and some solvent. But if it's 1, you're saying that everything that's in the solution is the solute, right? So 1 doesn't mean anything except as a summation. If you sum up all the mole fractions of your individual solutes, then they should add up to 1, right? Oh, and that's another point I didn't make. You can have only 1. solid, but you can have many solutes. Mole fraction, molality. Molality is a second cousin to molarity. Except in molality, which is a small m as the unit measure, is the same as molarity in terms of moles of solute. That's the same for both of them. But in molality, we're ratioing that moles of solute to kilograms of the solid. Like we're ratioing it to a mass. That means it's insensitive to temperature changes. And that's the one we're going to be using in our lab. We'll talk about it a little more later. Let's see, I already mentioned that. The nice thing about molarity, it's convenient because if I have, view it as an equation, right? If we have a value for molarity, and that's equal to moles per unit volume, and the volume has to be in liters, then if you know two of those, you can solve for the other one. So if you have, say I have a molar solution here of say 10 molar, and I want to be sure that I extract from that stock enough volume to give me 0.5 moles of the solute, right? So we know that I need 0.5 moles. Well, the unknown is volume, right? So you just solve for volume. I move V over here and 10 over there. 10 divided into 0.5 is 0.05 liters. Okay. Or how much would that be in milliliters? Let's see, let's make some room. On the floor, of course. All right, we're going to need some more places. 1, 2, 3. That's 50 milliliters. Okay. Remember, if this is liters, and the unit of measure is going to get smaller, right? Then the number has to get bigger. That's the way I keep myself straight. Instead of moving 3, I knew I needed to move 3 because there are 1,000 milliliters in a liter. But which direction do you move? Right? Well, if I know that big is going to small, then small has to go to big. So when I move 3 places, it has to go to the right. Otherwise, the ratio is wrong. Okay, that's how I keep it straight. All right, so that's the convenience of molarity. All right, so if we calculate the concentration of this 1 mole of table sugar in 125 milliliters, when we solve problems like this, and we did this in the first semester, I tell my class, word problems are designed to do what? Confuse, right? They're going to confuse you if you don't know the concept and how to find the parts of the problem that will solve it for you. So one way to do that is to extract information from the problem and put it on the board in a form that will fit into your solution. Right? We have N equals 1.00 moles, right? Okay. And volume equals 125 milliliters. And the question is, what's the molarity? Right? So we got everything extracted from the problem. Do we have everything we need? Yeah. Right. Except what? That's the wrong unit of measure. So in this case, we're going to go from small to big. That means this has to go from big to small. So the decimal has to go like that. So we actually have 0.0, excuse me, added an extra 0, 125 liters. And now we can calculate molarity as moles per 0.125 liters. And I think I got the answer here. I don't have to get the calculator out. So it's 8 moles. And let's see, we got 3 significant figures there, 3 there. This is a multiply divide problem, so 3 and 3 gives you 3 in your answer. 3 significant figures. Okay. Oh, got another problem. 10. Now we know the concentration of the solution. All right, I'm going to leave those up there. We're given the concentration at 10 molar, correct? Yep. What volume of the solution do you need to have 2 moles of sugar? So this is what we're looking for. Two zeros. So now this is the unknown. And if we look at our equation, right, solve for volume, it's moles divided by molarity. Right. So we have 2 moles divided by 10 molar. And that looks like 0.2, right? 3 significant figures. And that's liters. It didn't tell, the problem doesn't tell us what units to use. Right. But that will answer the question. How many milliliters is that? Right. You can do that in your head. 200. 1, 2, 3.
So how will we know, like, I guess it'll tell us what, if it's gonna be liters or milliliters? But just assume, excuse me.
But it has to always be liters, right?
To do the calculation, yes. If you if you need to input a value for volume, it's got to be liters. And if you're in this situation where you're calculating what the volume is, then moles and molarity will give you an answer in liters.
So just keep it in liters, don't change to milliliters, correct?
Well, a lot of my questions are multiple choice. So you look at the answers and that'll tell you what you need to do. Right.
Yeah. Okay.
If I have A, B, C, D, E, and I have answers in there, some of them are in milliliters and some of them are in liters, then you do your calculation and you get liters first, and then you look to see, are any of the liters match up? Yeah. Then you change it to milliliters and see if those, and probably one of those will match up. Okay. Problem solving techniques. Test taking techniques. All right. So now we're going to complicate things a little bit. And we've got 2 materials, sodium hydroxide and potassium chloride. All right. And we've got 100 grams of each one. Okay. Now we're going to put these in solution. And the final volume of the solution is going to be 250 milliliters. And so the volume for each one is 250. Yep, extra 0 milliliters. Okay. The question is, what's the concentration in molarity for each one? First of all, do you expect that they're going to be the same concentration in molarity? No. Why? Because, well, that's grams, that's grams. What would have to be the case if they were the same concentration? No, they have to be the same molar mass because we got to convert this to moles, right? So we need to do a dimensional analysis here. Grams on the bottom, moles on the top, so the grams will cancel and leave us with moles. Okay. Do you remember that in Chem 101? You didn't do dimensional analysis?
It's been 4 years, so
Oh,
I don't really
okay.
remember a whole lot.
Okay, you need to review dimensional analysis. It's just unit conversions. That's what we're doing. So, and the conversion, my mind's gone blank. Conversion factor, that's it. The conversion factor is equal to what? 1. Conversion factors are always equal to 1. Why? Because this value is equal in in some way to that value. And if you divide X by X, you get 1. That's why we can multiply any number of conversion factors. We can chain them together because they're all equal to 1. Okay, so what do we put in here? Sodium hydroxide. Well, we have to look up sodium. It's 23. Yeah, 23 grams per mole for sodium. Oxygen is 16 and hydrogen is 1.01. So we got 1 0 there. 40.01 grams per mole for sodium hydroxide. So that goes on the bottom. Why? Because we want to cancel the grams and leave us with moles. Okay.
So on the top it's moles and then the bottom.
Mhm.
Okay.
Now, if we had moles here and we wanted to make grams, it would we just flip it, right? It's equal to 1, so you can turn it upside down and it's still equal to 1. Okay, so 40 into 100. Let's see what that is. Let's see here. 100 divided by 40.01. I get 2.4994. 2.494. And that's moles. Now, notice in this calculation, you have 4 significant figures there and 4 there, and I'm keeping 5 here. You know, tell the newcomers why I do that.
For rounding purposes.
Yeah, rounding error. If you have more decimal points, then you are less likely to have rounding error if you have multiple steps in your calculation. So I keep them there until the very end, and then I round them off to the correct number of significant figures. So we do the same thing for potassium chloride. Right, grams on the bottom, moles on the top. We just need a molar mass. Potassium is 3910. I always use my molar masses. I always round them off to 2 decimal places. It's just easier that way. By the way, just as a reminder, when you have a conversion factor, I mentioned this one has 4 significant figures, but that doesn't matter. Conversion factors are blank mind again. Exact numbers. Sorry. Exact numbers, so they don't have an impact on the answer of significant figures. They're infinite number of significant figures, conversion factors. Right? Okay, so we're only focused on this one. So eventually we'll have to round it off to 4. All right, so we got 39 grams per mole in chlorine. Oh, I know that one. 3545. 5 and 14 and 74.55. There we go. So let's divide that one into 100. I get 1.3414. Okay, now we have the moles. We need volume in liters. Right, which way do I move the decimal?
To the
Right. This is going to get bigger, so that has to get smaller. Like that. Same for both of them. Now we can do the calculation. The molarity of this one is going to be 2.4994 moles per 0.2500 liters. Okay. Let's see, I just swap that one and then divide by 0.25. And I get 9.9975 molar. But I got to round it off to 4 places, right? 1, 2, 3, 4. 9.98. I think the solution, the problem solution in here rounds it off to 10. But this is the correct answer. And the molarity here is going to be number of moles, 3414, divided by 0.25. Actually, you know what, the other way to calculate this? Instead of dividing by 0.25, multiply by 4. You don't believe me? Okay, let's do it the long way. Let's go back there and divide by 0.25. 5.3655. And we have 4 significant figures, so it's 5.366. All right, what if I did 1.3414 multiplied by 4? 5.3656. How's that happen? Dividing by a quarter is the same as multiplying by 4. If you say this, turn that into a fraction. I'm teaching math today. 1.3414 and divide that by what is 0.25 equal in fractions? It's equal to a fourth, right? Correct? So the denominator of the denominator is the numerator. So that means this goes like that, and it's 4 times that. Okay.
I have a question.
Okay, sure.
So when I calculated up the 1 mole divided by the grams, I'm getting 0.0134. So why is it 1.3414? Like, are we just going to the first number?
Did you tell them the 100?
No.
Yeah, like you have to do the 100 grams and then that's times that fraction of 1 mole over 70.
Okay, I see what you're talking about now. Okay, I understand now.
Divide by.
Yeah, I thought it was just, I thought the 1 moles divided by the grams was just the equation itself. I didn't realize you had to multiply by 100.
Yeah.
Yeah, okay, I
Right.
see it now.
Mhm. So you can either divide by that value, or you can say, what's that fraction, and multiply by that value. It works too. Yeah, when you have a string of calculations like this, and you have values in the numerator and the denominator, calculating them, as far as your calculator is concerned, it doesn't matter if you do that one divided by that one times this one divided by that one, or times divide by divide. Works. It works. Your calculator doesn't care. Okay, let's see if I got the answers right. Yep, they rounded it off to 3. And then 5.37. There you go. So they are different molar concentrations, molarity concentrations. And the main reason, since everything else is equal, the reason is molar mass. They're different molar mass. All right, mass percent. Now, we used mass percent in the first semester, didn't we? For composition of compounds. Yeah, mass percent, like potassium chloride would be so much mass percent of potassium and so much mass percent of chlorine, and you add them together and you get 100%. So the analysis of compounds gives you a mass percent for the compound. But now we're talking about solutions. It's the same math. The math is identical, but the variables that you put into the calculation are a little different, because you want the mass of the solute, mass percent. Let's see. What else do I tell you about percent? It's a dimensionless number. If you don't know how it's calculated, then percent could mean anything. It's parts per 100. So what's parts and what's 100 parts, right? Is it mass volume? Is it mass? Is it volume? You don't know unless they tell you. So that's why when you see percent as a unit of concentration, ask yourself and then try to find out, is it mass divided by mass? That's complete. And in this case, it is mass divided by mass. So mass percent in this case would be the mass of the solute divided by the mass of the solution. Which also is the mass of the solute divided by the mass of the solute plus the mass of the solvent. Okay. Oops. It's percent. Times 100. Okay. If you just do this part, that's a fraction. Right. Times 100 gives you percent. All right. So let's see, we have an example here. We're going to dissolve 5.5 grams of glucose in 78.2 grams of water. What's the mass percent? Okay. The mass of the solute is 5.5 grams, right? Okay. What's the mass of the solution? It's 5.5 grams plus 78.2 grams. Times 100. Okay. And if we do our math correctly, it should be 6.6%. Percent mass. Now, if you buy beer or wine or booze of any kind, it's going to give you percent alcohol. Right? But they use percent ABV. What does that mean? Alcohol by volume. So that's going to be, say, milliliters of ethanol per 100 milliliters of solution. That will be alcohol by volume. Okay. It's an example of volume versus mass. Oops, skip one. No, okay. Mole fraction. Mole fraction is real simple, right? And we give it this fancy letter. I think in Greek, right? Does anybody know sororities and fraternities? The Greek letter here we use is chi, which is a big X. So the mole fraction of this component is equal to the moles of A divided by the total moles. Okay, that's it. It's a fraction. Now we're going to find out later that if we're talking about gases, the mole fraction of the gas, say if we wanted to know the mole fraction of oxygen, the mole fraction of oxygen in the atmosphere, then it would be the moles of O2 and the total moles of air, total moles. So that would be, for the most part, it would be oxygen and nitrogen combined. But that's also equal to the pressure of oxygen. Well, and we talked about partial pressure yet? Yeah, we did. Dalton. Yeah, we did partial pressure. So the mole fraction then would be the partial pressure of oxygen measured divided by the total pressure. That's a neat relationship because now we know all we have to do is measure the pressure of this, partial pressure of that, the total pressure, and we can calculate what's the mole fraction of oxygen in the atmosphere. All right. A solution of phosphoric acid. Okay. This is one of those. Now, the problem in this case gives you the formula for phosphoric acid. You're going to need that to do the calculation because we need the molar mass. But if we didn't, if the problem didn't give you that formula, how would you solve it? You have to know how to write the compound from the name, nomenclature. So phosphoric acid, we know, is this. That's hydrogen phosphate. In aqueous solution, now it's phosphoric acid. It's in solution. And we're going to dissolve 8 grams of this. Yeah, 8 grams of that in 100 milliliters of water. So that's the mass. And the volume is 100. And what we want to know is, in this case, in this problem, the mole fraction. So what would be the mole fraction? Well, we have to know something else too. We're given density for water. The density of water is 1 gram per milliliter. We have to assume that the solution is very close to that. Otherwise, we can't solve the problem. So we're saying the density is equal to 1 gram per milliliter. Now, usually when these acids become extremely concentrated, like sulfuric acid, we used to buy sulfuric acid concentrated at 98% by mass. Right? It was almost pure sulfuric acid, and it was heavy. A 2-liter bottle, three and a half liter, I think. But it was heavy. And that's characteristic of most of these acids. When they get really concentrated, they're more dense. But if they're diluted like this, then they're pretty close to water density. Okay, let's see. Calculate the mole fraction. All right. So what we need to know is the fraction, what the number of moles of sulfuric acid and the total moles. Right, so we got grams. We can calculate the moles of sulfuric acid pretty easy. Right? We just need the conversion factor. Right? Molar mass. Right? So hydrogen is going to be what? Hydrogen is 3 times 1.01 grams per mole. Phosphorus is 30.97. And there's only one of them. And oxygen is 4 times 16, which would be 64. Right? 16 times 4. Then we just add them up. This is an 8. I think that's right, 98. 31, 8. Isn't that right? Okay. 98 grams per mole. Okay, divide that into 8. 8 divided by 98 is 0.0816 moles of H3PO4. Now we need the moles of water that it's dissolved in. It's in 100 milliliters. You know what? That was misleading discussion because we know we're going to put it in 100 milliliters of water. So the density of water is accurate. It's only for water. It's not for the solution. Okay. I could have misled you there. So how do we calculate the number of moles of water? Well, we have 100 mils of water. We know the density. Remember, what's the formula for density? Mass per unit volume. Right? So if we have volume and density, we can find out the mass. What's the mass of water? Well, we can do that one in our head, right? 100 milliliters of water is going to be 100 grams, right? Because it's 1 gram per milliliter. So the mass of water equals 100, 100 grams. Now we need to convert that to moles. Anybody remember the molar mass of water? We did it so often, we gotta have it memorized. 18.02. All right, 2 hydrogens at 2.02, 1 oxygen at 16, add them together is 18.02. We're gonna divide that into 100. .5494. Moles. Okay, now we can calculate the mass per, the mole fraction. All right, we got this is our solute per total, which will also include that plus whatever the water is. And that'll be our mole fraction. Let's see here. Let me flip this. Duplicate that. This is 5.6310 divided into 0.086. Okay, so I got a mole fraction of 0.0145. Oh, and for the newbies, if I were to write this number like that, that's wrong. You never leave a dangling, an orphan decimal. If it's out here on the left, it needs to be bracketed in by another 0. Okay. Just word of the wise. Okay, so let's see if it agrees. 0.145. Yep. That's the mole fraction. Now let's see. We're going to do it. We're going to do it again. So I'm going to leave that stuff up there so that we can talk about molality. This was mole fraction. This is equal to mole fraction of H3PO4. Now we're going to introduce the concept of molality. Molality is moles of the solute, just like we did before, like moles of the solute here, that divided by kilograms of the solvent. Okay, so we know that we have 100 milliliters, 100 grams. So how many kilograms is that? Okay, the unit gets bigger by 1,000. So the number has to get smaller by 1,000. 1, 2, 3. Okay. Why do we use kilogram? Okay. How many, if we're talking about water, how many milliliters are there in a gram? 1. Okay. So if you have 1 gram of water equals 1 milliliter. What if we go up by 1,000 and make it 1,000 grams or a kilogram? Right? Kilogram. We would have to increase this one by 1,000, wouldn't we? So what's 1,000 milliliters? Liters. Molarity is moles per liter. Molality is moles per kilogram. The relationship there is liters to kilograms. But there's a subtle difference. In molarity, you have liters of solution. In molality, you have kilograms of solvent, not including the solvent, right? So that's a A subtle but important distinction. All right, so now that we have the definition, let's solve that same problem now for molality. So we have 0.1 kilogram. 0.100 kilogram of solvent, and we have 0.0816 moles of solute. So we can do that in our head. Like 0.816 molal. Right? Dividing by a tenth is the same as multiplying by 10. Right, so I just move the decimal place over one. Got it. No calculator needed. All right. Let me be sure they agree with me. Yeah. Okay, we're good. And notice the difference between the notation. So the problem is you have to know, are we talking about mass or are we talking about molality? Right? If we're talking about molality, then little m means that. Concentration. If we're talking about mass, then m means grams or kilograms, right? So that can be confusing too. You have to look at the context to see what little m stands for. Sometimes they write little m as an italic. I think this one is italic. Right, and that helps tell the difference. All right. No questions so far?
I do, but it's just like a real simple one.
Okay.
So when answering, so like on that one question, it was like 10.0. Do I always have to put the 0.0 or can I just put 10? Like
If
it's
okay.
a number.
If it's multiple choice, you won't have any choice.
Yeah.
Right. But if it's a fill in the blank or you have to show the calculation and that's the answer, then you need to be wary of significant figures. Right, so go back and review your significant figure rules. Right, there are two sets: multiply, divide, add, subtract. Most of our calculations are going to be multiply, divide. So that's why you can chain them all together and then resolve the significant figures at the end. It's only when you introduce add, subtract into the mix that you have to do intermediate calculations based on the PEMDAS rule. And we, unlike organic, we will have review sessions in this one. Yeah. Based upon the handout, the review problems. Yeah. Okay, let's look at a little bit of theory now about how solutions form. Now, to be sure, when a solution forms, it does all of these steps at once. We separate the steps, 1, 2, 3 in that slide, because that allows us to conceptualize the process. But as far as the solution is concerned, it just does what it wants to. It does them all at once. So what happens when you form a solution? We can divide it into 3 steps. Right? First step, take the solute bond breaking. And I don't mean covalent bonds. I mean the intermolecular bonds. The bonds that are holding molecules together, that are holding one molecule to another molecule. Right? The internal bonds, we don't mess with those, right? Because this is forming a solution. This is not a chemical reaction, so we can't break internal bonds. The intramolecular bonds are always intact. But the intermolecular bonds between the solute molecules, you have to break those. You have to put enough energy in to break those bonds and get those separate molecules available. Okay. This is, I think I went over this in class. Did I do this in organic too? Yeah, I did. Okay. The input of energy means this is positive, right? It's endothermic. You have to, it's cost you energy to get those things apart. The other step, second step, is we have to break bonds of the solid. Right? That also is endothermic. Right? So this is like a investment in a company. You're putting money in, but you haven't seen any output yet. When you put these two together, right, in step 3, you form spelling. You form the intermolecular bonds. Solvent to solvent. And this is an exothermic process. Okay, you get some energy back. Okay, when you do that, and you say, I put this much energy in here, that much energy in there, and I got this much back. If you want to know whether the overall process is endothermic or exothermic, right? Does the solution get cold or does it get warm? It's in the balance. You add these two together with their positive signs, and then the negative sign on this one, and what do you get? If you get a positive sign, then the solution is going to get cold because overall it's endothermic. If it's a negative value, then the heat of solution is going to be, it's going to get hot, exothermic. Okay, that 3-step process is a way of conceptualizing solution formation. And there it is in a pretty picture that the authors thought they probably paid a bunch of bucks for somebody to draw that for them. Okay, I already said this. Okay, that's the heat of solution, the enthalpy of solution. Now, if you, let's see, who works in a hospital situation? Yeah. Do you ever use the cold packs and hot packs? Yeah. What you've got in, there's a different salt in each one that goes into aqueous solution. One of them produces heat. It's an exothermic heat of solution. And the other one is endothermic.
Like hot hands, like the old ones that used to break the little tab.
That's different. That's a phase change. Right.
It was like instant, so the pouch inside of a pouch and invested, right? The one you're talking about?
Right, the one I'm talking about, right. The pouch inside the pouch contains the solid salt. And then around it is the water. So when you grab it and go and break it, then it mixes together. Right? And then the heat of solution is either endothermic or exothermic. The one you're thinking about where you do the clicker thing is you have a super saturated solution. And it's reasonably stable, which is unusual for super saturated solution, but it works with this one. And what you need is to stimulate the precipitation of that excess amount of salt that's dissolved in the water. And the clicker does that. Right? You need something to kickstart the precipitation because it's got more solute in it than it's theoretically able to hold at that temperature. And when it does that, its heat of solution is exothermic. I mean, not heat of solution, excuse me. It's when you go from individual ions, say you have a salt with cations and anions, and these are separate in aqueous solution, right? When they come together in that salt, the solid that you see forming, when they come together and produce this solid, Separated, they have more energy. They have lower energy here. So what they do is they give up. They give up energy to go from this high energy state to the low energy state. Okay. This is more stable, which means it's lower energy. And that's why it feels hot. But you can reset the pouch. It's just throw it in boiling water. And then it'll all go back into solution. And then until the next time you want to do your clicker thing and get hot again. It's absorbed energy from the water to go back this direction. Okay. So this enthalpy of solution, here's an expression where you have state functions. In other words, it doesn't matter how you got there. It's not a path function, it's a state function. And the reason for that is because enthalpy is a state function. We studied that along with entropy. Anyway, that's why you can add them together. And what comes to mind is Hess's law, where you can add these equations together and get a composite equation out of the individuals. Okay, explain why water and oil do not mix. All right, I'm going to leave that up there. So if we look at, let's say the solvent is water. And the solute is oil. Our proposed solute is oil. And we want to make a solution of oil and water. All right. What this table expresses is a comparison of the amount of energy required to accomplish that step, and get energy back here. So how much energy does it take to break those bonds? What type of intermolecular forces are involved here? For an oil, it's nonpolar, right? So it's not dipole. It has to be London dispersion forces. We talked about that, didn't we? Yeah, London dispersion. Very weak, very weak. So just a small amount of energy will get those oil molecules apart. Whereas water is hydrogen bonding. It takes a huge amount of energy here. Hydrogen bonding. Okay. What kind of interaction are you going to get between water and oil? Remember, even though water is hydrogen bound here, London dispersion forces are still there, right? They're a lot weaker than, so this is the major attractive forces, right? But London's still available. So the only thing that can happen between these two is London dispersion forces. Now, on this chart, we're looking at non-polar solute, right? That second one down, and a polar solvent. The H1, the delta H1, let me do this. 1, 2, and 3. So we can correlate them with that. The delta H1 is going to be very small. And the delta H2 is going to be very large. And the energy you get back is going to be very small. So when we add those all together, you get a large delta H positive. It cost you a lot of energy. You didn't get much of it back. So if it did form a solution, it would be cold, right? But you've tried to mix water and oil before, right? Make your own salad dressing, vinegar and oil, and maybe throw in some Mrs. Dash in those little jars that the chipped beef come in with the blue caps. Once you use them, just clean them up real good. It's perfect for one salad. Just fill it up however much ratio you want. Snap the cap and just shake it like crazy. And then pour it on your salad before it separates. But it doesn't get cold, does it? No, it doesn't get cold because no solution is formed. When you have a very large composite, delta H1 plus delta H2 plus delta H3 equals delta H total. When this one right here is huge, in a positive sense, if this is large positive, then you're not going to get a solution. There's one way to think about it. Let's say we used a different approach in organic. I can remember what that was. Even though you can get these things apart with a little bit of energy and a lot of energy here, what is to be gained when you expect a solution from them, right? Are there strong attractive forces between the solute and the solvent? No. The strength of the forces determines whether it forms a solution. And since the force magnitude is almost nothing with London dispersion, then you're not going to get a solution. They don't like each other. That's why like dissolves like. Now, if we have a situation, we could do it the other way, right? We could have a polar compound here and a nonpolar there, and you'd end up with the same situation. You have a large positive. But if we had a polar and a polar, and you put a lot of energy in, but when they come together, they're attracted to each other. They have those polar bonds available. You get that energy back. So when this is very small, then to use an anthropomorphic term, they like each other. They form the bonds to make the solution. Now, when you've got nonpolar and nonpolar, it takes just a tiny amount of energy to break those bonds, but they have available London dispersion forces to hold them together. They like each other. Now, the like is not as strong as the polar, but it's still strong enough compared to what they had to put in to get them apart. Okay? So, if this is a large positive value, you're not going to get a solution. If it's a small value, you will get a solution. Questions? Okay. We'll move on then. Okay. Oh, we did mention in our organic discussions the concept of entropy in the formation of solution. If the entropy increases, then overall for the system, then you have more tendency to form a solution. So the way we look at that is, if you have, say, oil and water, what it's going to do is have water on the bottom and oil on the top, right? This is going to be the same volume it was when you put them together, same volume when you put them together. Their entropy hasn't increased at all, because this has the same number of microstates in that volume as this one does. But if you put water and salt together, right? And you put the salt in there, it's gonna go into solution. Its entropy is gonna increase dramatically. Okay, and that is another driving force for the formation of the solution. Now, that's not in my slides, but I thought I'd throw it in there to make the connection with entropy. Okay. Solubility. We've sort of hammered this one pretty hard already. Polarity, structural effects, and what produces polarity in molecules and polarity of the solvent will have an impact on solubility. So a polar solvent will dissolve a polar solute, and a nonpolar solvent will dissolve a nonpolar solute. And like always, there's gray area in between. And I mentioned this yesterday. Have you ever seen a dirty, oily engine cleaned, steam cleaned? You got the technician comes out wearing these protective clothes and these big gauntlets, and he's got this steam wand in his hand, and his face is covered with protection, a mask. And they turn on the generator, and steam comes out of the tip of that thing at high pressure, and it's hot enough that it would cut your arm in half. So he goes after the engine and starts cleaning it off, and lo and behold, all that grease and dirt comes sloughing off. Two effects there. It's so hot that the oil is melted, it's decreased viscosity and just runs off the engine. But the other effect that we don't think about is that at that temperature, you can get some of that oil dissolved in the water until it cools down. There's a sufficient energy in there to, well, let's think of it in terms of entropy. If you can get some of that oil dissolved in the water, its entropy increases by quite a bit. But it takes a lot of energy to get there. That's not going to be on an exam if you're wondering. Sometimes it's hard to tell. What are some pressure effects for solubility? How much of a gas will go into solution under various pressure regimes? Now, if you put pressure on a solute and solvent, and they're both solid, no impact at all. They won't change their solubility. Or a liquid and a liquid won't change their solubility. A solid and a liquid have no effect. When there's a gas involved, pressure makes a difference. And for that, we quantify that with Henry's law. I think that was his last name. He probably had two first names. So there's Henry's law. The concentration of the dissolved gas in solution is proportional to the pressure of the gas above the solute. And then you have a proportionality factor that figures in. Now, this constant has to be determined for every situation of solvent and solute. But we can treat this like our gas laws. Remember when we did those? If that's a constant, then we've got, and this is one and that's one, at this pressure and this concentration, right, divided by pressure, that's equal to a constant. Well, all we have to do is change the pressure. Say increase or decrease the pressure, it'll change the concentration. But there's still, the ratio is still equal to that constant. That means the initial divided by the initial equals the final divided by the final. So that makes it easier to use where you don't have to calculate constant. That's not in here, but if you ever have to do that, that's the way you'd handle it. Henry's law. Okay, that's Henry's law. And since there's no temperature involved, in fact, the K is temperature sensitive. Right? If the temperature changes, then that solubility constant will change. Oh, units of measure. Units measure whatever you want it to be. Atmospheres, millimeters, mercury, molarity, mole fraction. As long as they're the same on both sides, then you're good to go. It's only when you introduce temperature as a factor that it needs to be Kelvin. Okay, temperature effects affecting aqueous solutions. We're going to look at that in just a second. These structural effects, if we go back to Lewis dot structures and how we use them to determine geometry, which leads us to a conclusion of whether a molecule is polar or nonpolar, then that's where the structural effects come in. And they produce either nonpolar or polar, generally speaking, molecules. The nonpolar substances are hydrophobic. And that word just means I'm afraid of water. I don't like water. Hydrophilic means I love water. So they'll dissolve in water. Let's see, we talked about it already. So why does more gas go into the solution under higher pressure? Well, if we increase the pressure by decreasing the volume above the headspace, that's the easiest way. Just use Boyle's law. Change the volume and you change the pressure. So we decrease the volume and increase the pressure. What you're doing is you're as the gas, let's see, put our frictionless piston here. We've got a liquid here, and we've got gas molecules up here. Even before you change the volume, you've got an exchange of gas molecules here into and out of solution. Okay, that's what we call equilibrium. It's happening at the same rate. Dissolution and evaporation are both happening at the same rate for that particular gas. But if we decrease the volume, now we're increasing the number of impacts because they're the same number of moles at the same temperature, but they've got less surface area. So it means you have more impacts from each one on the given surface. That includes the walls, that includes the piston, that includes the surface of the liquid. So if you have more impacts, you're going to have more of them going into solution. And you have to reestablish the equilibrium. And you do that, we could use Le Chatelier's principle here. We've stressed the system. Right? How does it respond? Well, it responds by decreasing the pressure above here. And it decreases the pressure by reducing the number of moles of gas in that space. And the way it does that is it puts more of them in solution. Okay. So when you open a bottle of pop, especially if it's been sitting out on the picnic table for 30 or 40 minutes in 85-degree weather, when you crack the top of that, it goes, there goes all your carbonation. Right? At that temperature, it's not very soluble, but it's under pressure. It's got a lot of pressure against it. So it stays in solution until you do something. Right? Well, it's two things. You can crack the cap or you can drop it on the ground. And then you don't want to open it. Or you'll have a fountain like that. But that's why Henry's law works. That's the theoretical explanation for Henry's law. Remember, laws don't say why. Laws just say this is what happens. And what we're trying to explain is in a kinetic molecular way of explaining it is if you decrease the volume, you increase the number of impacts, you get more of those molecules in solution. Now, how about temperature effects? Well, if you're dissolving a solid solute in a liquid, generally speaking, the higher the temperature, the more solid will go into solution. There are exceptions. There are some, particularly salts. There's some salts that are less soluble in warmer solutions. Not many, but there are a few. And the explanation is not really convincing yet. So I'm not going to bore you with that. But for gases, if we keep the volume constant now, and we say, all right, what happens to the solubility of that gas if we change the temperature, right? If we change the temperature and we go up to a higher temperature, right, increase, what happens? Well, from a kinetic molecular theory side, you find that if you increase the temperature of the solution, you're increasing kinetic energy of all the molecules in that solution, right? You will increase the vapor pressure of the liquid, right? So you'll have more of these the solvent molecules in the vapor phase, but you'll also increase the kinetic energy of the solute molecules, and they'll go into the vapor phase. I mean, up here in this headspace. So you're decreasing the concentration of the dissolved gas in this liquid by increasing the temperature. And that's consistent across any solution of a gas in a liquid. That's why your soda pop at 85 degrees on your picnic bench, when you crack it, it goes whoosh, because more of that, less gas is in solution, more of it is in the headspace under extreme pressure. So what I do is I take my 2-liter bottle, I stick it in the refrigerator for a couple hours, cool it down. Then when you crack the top, it goes shh, and you got most of your carbonation still in solution. All right. So solubility of solids as a function of temperature, it varies all over the place. Sugar has a fairly steep solubility curve for solubility versus temperature. Potassium nitrate has a very steep slope. Sodium nitrate is about the same as sugar. And then sodium bromide and potassium chloride, they do increase solubility, but it's not as steep a slope. In other words, raise the temperature and you don't get as large an increase of solubility. Now you got these other two, sodium sulfate and cerium sulfate, go the opposite way. You increase the temperature and they become less soluble. And this, at this point, that's the only way to tell the difference. It's an engineering table. You just have to do the experiments and see what their solubility is. All right. And here it is for gases. Right? Solubility of gases. 10 to the minus third mole per liter. Molarity, right? Yep. Thousandths of a mole per liter. So as you increase the temperature, methane goes down, oxygen goes down, carbon monoxide, nitrogen, all of them go down. Helium is one of those special. It starts out real low, right? It's like 0.5 or 1 times 10 to the minus, no, 5 times 10 to the minus 4 molarity. Very low solubility. And it doesn't decrease a whole lot as you increase the temperature. We used to use that characteristic of helium in our liquid chromatographs. When we have a high pressure liquid chromatograph, what you're doing is you're trying to force a mobile phase, a solution, through a column of solid particles. And it takes a lot of pressure because these particles are very small and the spaces in between are very small. So it takes a lot of pressure, 100 atmospheres. So if you did that with a solution, a mobile phase that has dissolved gas in it, like nitrogen or oxygen, and when you get to the other side and the solution comes out the other side and you want to send it to your detector to see what's in that fraction, this is chromatography, then what's going to happen when the pressure is released? All that dissolved gas is going to just come right out of solution under less pressure and wreak havoc on your detector. So what you want to do is get rid of as much of the dissolved gas as possible. And one of the ways we did it was a process called sparging. We take these, you've seen these little air stones in aquariums We put those on the end of a tube and blow helium through it and stick that into our mobile phase bottle. And we sparge it for about 15 or 20 minutes. And what it does is the helium competes with all the other dissolved gases for space in that solution. And it drives all the other gases out and leaves just a tiny amount of helium. Right? It's the helium concentration is so small that it doesn't have an impact on your detector. So that's one way to clean up your mobile phase of dissolved gases. The other way now that a lot of them are using is countercurrent flow. They have this membrane and you pump your solution past the membrane. And on the other side of the membrane is a vacuum. They're pulling a vacuum. So the gases in this one under that low pressure are going to pass through that membrane and they're gone. And then your degassed solution goes on to the chromatograph. That's probably more efficient anyway, as long as the membrane is durable. Okay, there's enough of that. This experiment is a demonstration of the migration into vapor phase of the solute and its deposit, its solubility in another solution. Well, actually, I wish it were, but it's not. We got this bell jar and we have water, pure water in one side and an aqueous solution in the other side. Right? So what are they going to do? Who's got the higher vapor pressure? The pure water. Pure water has the higher vapor pressure because the solute in the solution side is preventing some of those water molecules from vaporizing. So the vapor pressure from the solution side is lower than it is for the water side. So more water molecules are entering that vapor phase, and they're now trying to establish equilibrium with that concentrated solution on the right. So more of them are going into that solution. And if you let it go long enough, all of your water molecules from the left side are going to end up in the right side. The best way to do that, and the way I've seen it done that works the best, is to have a concentrated sulfuric acid solution on one side, pure water on the other. And probably within 24 hours, the pure water is gone. It's all over in the other side. Okay. Vapor pressure. I mentioned this one earlier, so it shouldn't take too long to cover this topic. Any pure substance, any pure, let's talk about liquids. Any pure liquid has a tendency for the molecules to leave the surface of the liquid and enter the vapor phase. Right. So if we have a closed container, let's draw an Erlenmeyer flask here. Right. We have a closed container of some pure substance like water, and we put a stopper in the top. Then in the beginning, what you're going to have is evaporation only, right? Because there's none up here. So some of those are going to leave that solution and enter the vapor phase. But eventually you get some up here, and at any given temperature, they're going to start to return. Now we're working toward an equilibrium. When equilibrium has been established, where the evaporation and the condensation are equal rates, then we have a pressure up here that is characteristic of the molecule itself. So if the molecules down here are polar and they have a very strong attraction to each other, the vapor pressure up here is going to be low because very few of these are going to leave the surface. I mean, they're perfectly happy down here with their neighbors. But if the intermolecular forces here are very low, like say you only have London dispersion forces available, like you have hexane maybe, or one of those organic solvents down here, then a lot of those are going to go into solution before you establish an equal rate. So the vapor pressure of the pure is an indicator of the strength of intermolecular forces. Okay. Now, what happens if this pure liquid we use as a solvent, and we put a non-volatile solute in it, like say it's water, and we dissolve sodium chloride in it. Sodium chloride is not going to vaporize. What happens to the vapor pressure? Well, you've got those sodium chloride ions down here also attracting the water molecules very strongly. So they prevent some of those water molecules from escaping. They're being held in place. Plus, at the surface, you don't just have water molecules anymore. You have water molecules and ions from the sodium chloride. So it's a hindrance at the surface from escaping. So the vapor pressure should go down as you increase the amount of dissolved solute. And the expression for that is Rayleigh's law. Right? The final pressure that you could measure, right here, the pressure of the solution is equal to the pure solvent pressure. And this just means under standard conditions. So this one would have to be standard conditions also. And the magic number here, the conversion factor, is the mole fraction. The mole fraction of the solvent. So if we add some solute to it, the mole fraction of the solvent is going to go down. If we add just a little bit, maybe it'll be 0.9 or 0.8. If it's hummingbird feeder food, it might be 0.4. And you can calculate the expected vapor pressure of the solution if you know the mole fraction and the pure solvent vapor pressure. Now that's when the solute is non-volatile. Non-volatile solute. It doesn't contribute to the vapor pressure at all. Okay. And that's what it would look like on solution vapor pressure. If you had 0 mole fractions for the solvent, of course, the vapor pressure is going to be 0 because there's nothing there. But it gradually increases. And the ideal situation is a straight line. It goes from 0 to some value if it toward the pure. So the right-hand side for the mole fraction of 1 is going to give you pure, because that's 1 pure value. There we go. Now, what happens if you have a volatile solute? Then we have to modify the Rayleigh's law to include both the effect of the solvent vaporization and the solute vaporization. And all you have to do then is say, all right, we also need to know the pure solute vapor pressure. So we would add the mole fraction of the solute times its pure vapor pressure. And that would be a situation where you have 1 solute and 1 solvent. Okay. Which is the simplest situation. But you could extend this out, kind of like Dalton's law of partial pressures. You can go out as many as you need. They're additive. And the graph on the left, notice that the mole fraction of A goes to the right, increasing. Mole fraction of B increases to the left. So if this were A and this were B, then the red line, partial pressure of A would increase that way, and the partial pressure of B would increase the other direction. Okay. And if you draw those in on the same graph, you get 2 lines. And this goes back to a discussion of calculus, which I'm not going to do. But it's additive. In other words, the value of partial pressure of A and B at any given point along that line, if you add them together, you get the green line. Now, this is ideal behavior. Okay. Ideal behavior. So what do we mean by ideal behavior? It's similar to an ideal gas. In other words, the individual parts, the solvent and the solute, have no impact on each other in terms of partial pressure. Okay. And the way you get that is the intermolecular forces of the solvent and the solute are similar to the intermolecular forces between the two are similar to the forces of A with itself and B with itself. If they're of the same magnitude, then you get an ideal behavior. But if you put these two together, you find that if the intermolecular attraction between the two in solution is less than it is for either one individually by itself, then you get this convex vapor pressure. You get that deviation. However, if you put them together in solution and the attraction between A and B is a lot stronger than it is for A by itself and B by itself, you get the concave deviation. Okay, and that's what this graph is trying to show. And examples, right? Benzene and toluene are nonpolar, both of them. And their attractions in solution are about the same as they are as individuals. Whereas acetone in water, the attraction of acetone molecules with themselves is at a certain level, and water is at a certain level. When you put them together, then the attraction between acetone and water is much stronger. So you get a negative deviation. And ethanol and hexane, which are soluble in one another, but the attraction between ethanol and hexane is not as strong as it is of ethanol to ethanol and hexane to hexane. So you get a positive deviation for that one. Okay. I'm going to run out of time if I don't move it along. Would you expect, which one of these would you expect to be ideal, and which one positive, and which one negative? All right, maybe we can knock this one out in a hurry, because we still have to talk about colligative properties so that we can do the lab. All right, hexane and chloroform. Hexane is this molecule, C6H14. Okay. And chloroform is CHCl3. Let's see, ethyl alcohol, C2H5OH, and water, H2O. Okay. And hexane and octane. So here's hexane again. And this is octane that you burn in your gas tank. 18. That's why they give it an octane rating. It's based upon pure octane. 100 is the standard, pure octane. Okay, so if we put these two together in solution, what type of deviation are we going to see, or are we going to see an ideal behavior? All right. Well, what kind of attraction do you have here? London dispersion only, right? This is a polar molecule. Right? If we draw the molecule like this, hydrogen here, we have a chlorine here, we have a chlorine in the back, and we have a chlorine here. So chlorine is going to, the polar bonds are going to be this way, and overall it's going to be polar that way, right? So the attractions here are much stronger than they would be in solution. Right? Solution is going to be weaker attraction So we should get a convex deviation. Oops. Can't spell today. So the deviation is going to be like that over our line. How about ethanol and water? Well, we've got hydrogen bonding here. We've got hydrogen bonding there. We got hydrogen bonding. Well, how about the strength of the hydrogen bond? And this one, you've got two hydrogens to that oxygen. Here, you only got one with a bigger molecule on that side. So I would think that the attraction would be that, I'll tell you what, I'm thinking the attraction here between the two is about the same as it is individually. So this one should be ideal, right? By process of elimination, this one should be concave. The attraction between ethanol and water is not as great as water with itself, ethanol with itself. Let me see if I got even close. Oh, it didn't. I didn't put the answers in there. All right, you have to take my word for it.
So basically, excuse me, so basically you want something that kind of is proportionate rather than a lot more offset. Is that what you mean? So like you said, like the one only have one hydrogen, the other one have
Yeah, with two places for hydrogen bonding to occur, right? The hydrogen bonding forces should be stronger for this one. Right, and there's only one place for hydrogen bonding here. So when you put them together, you've only got one against this one. And the strength of attraction overall is less than it is for both of them as separate. So this one would be very high, this one would be a certain amount. But when you put them together, you're not going to get the same type of increase here because you don't have as many of these available. You've diluted out the water molecules by putting this in it. So you don't get that strength of attraction that you saw before. And that gives you the negative deviation. Okay, now colligative properties. There are a bunch of colligative properties. We're only going to talk about these four. So first of all, what is a colligative property? Well, I've tried to make sense of that word before, but I'm just going to have to go with the definition. Colligative is in reference to solution properties, is the property of a solution that is dependent on the concentration of the solute, not on its identity. So if you get something in solution, the property that you're measuring will change with the concentration of the solute. And you don't have to know what the solute is. So that may sound like a bad thing, but actually, in many cases, it's a good thing. Remember when we were determining the empirical formula, and then we used that to go to the molecular formula? We went to the molecular formula because we were given the molar mass of the true molecule. And we could compare the empirical mass with the molar mass and find out what that N was, the ratio. Well, how did they do that? Colligative properties. You can determine the molar mass of a substance without knowing what it is. If it lends itself to one of these colligative properties. Okay, so let's look at each one. We know about boiling point elevation and freezing point depression, right? Because we all drive cars. And antifreeze is put in our radiator, not just to transfer heat from the engine and to the radiator, but the boiling point of 50% ethylene glycol in our radiator is much higher than 100 degrees. So that keeps it from boiling when it gets really hot. And then in the winter, the freezing point is depressed. So it won't freeze at -20 degrees. Those are colligative properties, and they're based solely upon the concentration of ethylene glycol. In fact, you can use anything you want to. Ethylene glycol is used because it's extremely soluble, right? It's easy to produce, it's cheap. And well, that's enough reason right there. Another colligative property is osmotic pressure. You guys heard about that, I'm sure, in biology class or A&P. Osmotic pressure, isotonic, hypertonic, hypotonic, right? That refers to osmotic pressure. We'll have a slide on that in a minute. And then vapor pressure is a colligative property. So when we measure those vapor pressures, we actually don't have to know what the substance is you're dissolving in the solvent. You just have to know how much of it there is, or you can calculate how much of it there is by determining that difference between vapor pressures, right? For instance, if we dissolved a non-volatile solute in a solvent, and we know the solvent pure solvent pressure, and we measure a pressure of the solution, then this becomes our unknown. And we can solve for that value if we measure those two. So if you know the mole fraction of the solute, calculate the mole fraction from this, 1 minus that. Then you know the mole fraction, and now all you need to know is the total moles. If you know the total moles, then you can calculate the moles of your solute. All right, boiling point elevation. Here's the formula that goes with that. The boiling point elevation and the freezing point depression have similar structures mathematically. You're looking for a difference in temperature. So boiling point elevation. You're looking for a difference in temperature. So what do we mean by that? What do you mean by difference in temperature? The different, yeah.
The temperature change?
Yeah, that's what delta means. But what is it changing from and to? It's changing from what is the boiling point of the pure solvent versus the boiling point of the solution. So you would subtract, this would be temperature, boiling point temperature of the solvent, and subtract the boiling point temperature of the solution. And we're only interested in the magnitude, right? We know it's going to be an elevated temperature here. So if we subtract it from here, or if we put this one on this side and subtract that from, it doesn't matter. We want the absolute value. So actually we should do this. That would be accurate. The absolute change in temperature between the two. And that's equal to some constant, this boiling point elevation constant for the solvent. And it's different for every solvent. That has to be given to you, has to be determined independently. But once it is, then what we need to know is the molality of the solute. Right? We have to use molality because we're looking at a temperature change. If this were molarity, all bets are off. Okay. So that's the structure of this calculation. And if we run our experiment, which we're going to do, well, not with boiling point, we're going to do it with freezing point. So maybe I ought to move on to that. Let me go to freezing point next. And all we have to do to use freezing point is just change this to this. The constant for freezing point. And for the same solvent this K is going to be different for a freezing point calculation or a boiling point calculation. They're unique for each solvent. So what does that tell us? Well, if we look at the units of measure, and by the way, this temperature is degrees Celsius. You don't have to change it to Kelvin. Okay, degrees Celsius. And this is going to be what? Moles per moles of solute per kilogram of solvent. Okay. So if we look at the units of measure, how do we get from here to here? That tells you what the constant needs to be. In other words, if you want degree C here, it needs to be degree C here in the numerator. And it needs to be moles of solute here. And it needs to be kilograms up here. That way, kilograms cancel, moles cancel, and you're left with degree C. So the units of measure for your K are going to be usually degrees C, kilograms per mole. Or sometimes it's degrees C per molality. Right? This kilograms in the numerator, moles in the denominator is the inverse of molality. That's why molality goes in the denominator. So if you get in the habit of when you see a formula, if you look at the units of measure, then you can get a better handle on how the calculation runs. Right? Are the units of measure correct? And if we took it the other way and looked at this value and say, okay, I know the value here is going to be degree C, kilogram moles. And what does this have to be? I know that has to be moles per kilogram in order to cancel that and leave it with this. You can look at it several ways. So what we're going to do is we're going to run our experiment with pure lauric acid, which is a fatty acid. And that's going to be our solvent. And we're going to determine the freezing point of that solvent, lauric acid, pure. And then we're going to add a known mass of benzoic acid to it and remelt it and let it freeze again and check the temperatures. Read the temperatures over a time period and then draw a graph. And it'll probably over time, degrees C, it'll go like that, and like that to give us our freezing point. You do that for both of them. And then once you find the freezing point, under both conditions, you subtract one from the other and throw away the negative sign, if you have one. And then that goes in here. And then this value is given in the method. And then you solve for the molality of the solute. So once you got that value, this molality of your solute, that's moles of solute per kilogram of solvent. Okay. When we first set it up to do the pure solvent, the lauric acid, we put it on the balance and we know the mass. You just be sure that it's in kilograms and you multiply kilograms here of your solvent, right? And you get moles of your solute. Okay, moles of your solute. You also know the mass of your solute too, don't you? Because you added that to the tube, given a known mass. So what can you do with that? Molar mass is mass divided by moles. We got moles from here. We got mass from measuring in the balance. We can calculate the molar mass of benzoic acid. So I did part of the lab there already. That'll save us some time later. Okay, those two colligative properties are related, at least mathematically. And then we're going to look at osmotic pressure. let's see, freezing point depression. I forgot to go to that slide, didn't I? Okay, we'll leave it up there for a few seconds. And then we'll move on. This is an attempt at explaining why the difference in the two using this phase diagram. Actually, it's not a phase diagram. It's a pressure temperature relationship. And as you increase the temperature, if we look at the pure water one, the red line, you get, this is a phase diagram. Yeah, this is a phase diagram. We talked about that one last time, didn't we? Phase diagrams. Okay, so on the left, over here, is the solid, right? In the middle is the liquid, and over here is the gas. So this is the triple point right here. And if we take the pure substance, we get this trace for each of the phase changes. But if we put, if we're going to measure boiling point, we're dealing with vapor pressure. So what happens is if you add something to that water, it depresses the pressure, the vapor pressure at any given temperature. So that's why the blue line is lower than the red line. You're decreasing the vapor pressure. Okay. And on the left, if you add substance to your solution, it's a little more difficult to explain, but kinetically, let's put it this way. When you've got solutes in there with your solvent, then there's less opportunity for the solvent molecules to aggregate in a solid. It's interfering with them. So that line then is moved to the left. When you draw it all out, it's interesting though that the sublimation line on the far left down the low side didn't change at all. But for the vapor pressure, you're looking at a change in temperature at the boiling point. So 1 atmosphere at the top, you look at the blue line and the red line, and you see that delta T. And for the melting point, you see the red line and the blue line on the left, and that difference is the delta T for the freezing point. Okay, I've only got 15 minutes left and not enough time to do it. Let's see if we even need to do this one. A solution was prepared by dissolving 25 grams of glucose in 200 milliliters of water, or 200 grams of water. Molar mass of glucose is 180.16. That's true. What's the boiling point of the solution in degrees C? Okay. All right. One thing that we haven't talked about yet is when you put something in solution, we're not talking about just the moles of the compound. We're talking about the moles of the particles. So molecular compounds, when they go in solution, they stay intact. So if you put a mole of sucrose in water, you got a mole of sucrose dissolved in water. But if you put a mole of sodium chloride in water, how many particles do you have? 2. You have 2 particles. So you have to consider that also. And let me see. I'm going to flip ahead just a couple. Yeah, we're going to get to it. Okay. I want to steal my own thunder. Okay, so we're given 25 grams of glucose and 200 grams of water. So the mass of the glucose is equal to 25 grams. Okay. And the mass of the water is 200 grams. Mass of the water, which is the solvent, is 200 grams. Okay. Now, why do we need to know the molar mass of glucose? Because the only mass we're interested in is the mass of the solvent. Like, we want to know the moles of glucose. It's the solute. So we got to convert this to moles. That'd be 180.16 there. Let's go ahead and calculate that. 25 divided by 180.16. I got 0.1388. 0.1388 moles of glucose. Okay. So what's the mass here? Well, it needs to be in kilograms, doesn't it? Units get bigger, number gets smaller. Now we can calculate the molality of the glucose. It's 0.1388 moles per 0.200 kilograms, right? Ooh. Try that again. There we go. 0.6938 molal. Okay, how's that going to help us answer the question? We want to know what's the boiling point of the new solution. Well, what's the boiling point of pure water? Temperature, BP for water is 100 degrees. Okay. What's the temperature of the solution? Boiling point of the solution. That's unknown. Okay, so which colligative property is it? It's this one. Delta T boiling point equals K for the boiling point times molality. Oh, we were not given the K, were we? We can't solve the problem until we know the K. So let's find out what the K is. Let's see. I want to know see if this will give it to me. Ah, here we go. No. Here it is, yeah. Okay, so this value, I just looked it up. This value here is 0.512. That's degrees C per molal, right? Or it's degrees C kilograms per mole. And the molality is 0.1388 moles per kilogram. Okay, that's molality. And what we got over here is the absolute value of 100 degrees minus, excuse me, not delta, minus the boiling point of the solution. There we go. Now, if we solve that equation, what do we got? Well, we have to multiply 0.512 enter 0.1388. Oh, no, sorry. Wrong value. You guys gonna let me get away with that? There we go. That's the molality. Let's start over again. 5, 2, 8, 6. So this side is 0.3552. Okay. So this is the elevation, this is the difference, the elevation of temperature over the pure boiling point. So the boiling point now is going to be that plus 100. 100.36. So we didn't increase the boiling point by that much. Some. Rounding error. Okay. Explanations?
Yeah, where do we get the 0.3552 at?
Oh,
Oh, adding that together.
multiply.
Or multiplying, yeah, okay.
Yeah. And then since this is absolute, and I know that the boiling point is going to be higher, I knew that all I had to do was add that to that. Okay. Right. And we'll use the similar approach to melting point. Only with a different end game. This was just to determine what's the new boiling point. We're going to measure that. We're going to measure the new freezing point and use that to give us moles of solute. All right, here's that correction factor. If we have let's use freezing point. Let's say we have a change in temperature for the freezing point is equal to our constant for the freezing point of the solvent, and then the molality of solute. If the molality is a certain value, but when you put it in, if so many moles of the compound in solution, but it dissociates when you put it in solution, then you need a factor to compensate that value. And that's where the Van Hoff correction factor is located. Now, theoretically, if you have something like sodium chloride, its I would be 2. Because for every one of these, you get 2 ions. If we had something like sodium sulfate, like that, you have one of these, that's a polyatomic, so you only have one of those, I would be equal to 3. Let's stay with sodium. If instead it's associated with phosphate, then our I would be 4. Because for every one, you make 4 ions. Now, as a practical matter, well, for our purposes, this is good enough. But if you're an engineer and you need to be a little more accurate with your calculations, you need to take into account deviations from these values. And most of them are going to occur in terms of ion pairing. So if you have an ionic solid that goes in solution, and while it's in solution, if it's very dilute, right, then ion pairing is not an issue. But as you get more concentrated in the solute, then you have the opportunity for occasionally these 2 ions to repair, but stay in solution. And that would decrease that value by a small amount. And the more concentrated you get, the smaller this I gets because of ion pairing. Because that reduces the total number of moles of particles in the solution. There's our examples. And I already told you that. It's also more important for highly charged ions. So if we put, let's see, think of an example. How about, I'm assuming that this is soluble. Aluminum phosphate. So this would be 3, excuse me, no. Oh, no, that's not a good example. How about magnesium phosphate? This would be 2, this would be 3. So if all that goes into solution, you would get a factor of 5, right? 3 of these and 2 of those. But with the higher charge, you get ion pairing at lower concentrations. Simply because of the electrostatic attraction for higher charges. That's what that statement is trying to say at the very last, that last statement. So for more positives and more negatives on the ion, in combination with the size of the ion, because if the ion shrinks, you're concentrating that charge in a smaller volume, and the intensity is greater. So those factors play in to actually calculating the ion pairing factor, the Van't Hoff factor. So that would be the modified version. Let's see. Well, we do have lab time today, so I think we can bleed over a little bit. If you take 20 grams of sucrose and sodium chloride mixture and dissolve it in 1 liter of water, that's both of them are going into the same solution. The freezing point of the solution is found to be minus 0.426. So you depress the freezing point by adding 20 grams of sucrose, a combination of 20 grams of sucrose and sodium chloride. So we don't even know what the composition is yet. The freezing point of the solution is found to be minus 0.426. You've depressed it by 0.426 degrees. So if we assume ideal behavior, what's the mass percent composition and what's the mole fraction of sucrose in the original mixture? All right, this is going to take some algebra. All right, those are the important factors that you need. And that's why I put it in the slides. We know the total mass of the mixture is 20 grams. So when we move down, and we know the freezing point of the solution is minus 0.426. If we let the mass of the sucrose equal X, now why would we let sucrose equal X and not sodium chloride? Well, it goes back to the problem. The mole fraction of sucrose, or the mass percent of sucrose. So we're going to let X be the mass of sucrose, and then what's the mass of sodium chloride? 20 minus X, right? Okay. The molar mass of sucrose is 342.34 grams. It's a big molecule. And the moles of sucrose then would be the mass of the sucrose divided by the molar mass, right? Let's see, is that right? X grams divided by something grams per mole. That give you moles? Yeah. Numerator, denominator, numerator. Right? So that's good. Just checking. So that's our first algebraic expression. That would calculate the moles of sucrose. The mass of sodium chloride then would be 20 minus X, And its molar mass is 58.45. So we divide that into 20 minus X, and we get the moles of sodium chloride. Okay, so the molality of the solution is the summation of those two moles in sucrose and sodium chloride, or their equivalents. So the moles of sucrose is X divided by 342 plus the expression for the moles of sodium chloride. Right there. We're taking this one, put it here, this one, put it here. That's moles of the solvents, the solutes. And then this is the mass of the solvent, which is 1 kilogram. Right? Isn't that the problem? Yeah, 1 liter of water, 1 kilogram. Okay, so that's where we are at this slide. We're going to go to the next slide and take that with us with this discussion. When we use the formula to calculate the molality of the solution, the Van Hoff factor is only 1 for sucrose, but it's 2 for sodium chloride. So how do we deal with that? Well, the difference in temperature is 0.426. We know that. And the KF is 1.86. It was 0.512, I think, for the boiling point, but it's 1.86 for the freezing point depression. So the different values. All right. So what we find is the formula is that delta T is 0.426 and the K is 1.86. And the I we're using is a composite. The I and the molality is a composite of the two. So what we're saying, this is the trick to this whole problem. That IM term in our equation is, once we solve it, it's equal to 0.2290. So that would be 0.426 divided by 1.86. That's where that came from. Well, what's that IM? Well, the IM is the I for sucrose times its moles, its molality. And the I for sodium chloride times its molality. Add them together, and that's what that equals. Now that we have an equation with one unknown, we can solve for the X. I think that's the central trick to this whole equation, knowing that you can do that. You can sum those two. And then on the next slide, we're going to solve for the X, and it turns out the X is 14.55 grams of sucrose. And that makes sodium chloride 5.45. And then it's a simple matter of calculating mass percent there. That's busy work. But it also wants to know mole fraction. So we got the mole fraction, and that's what that X means, mole fraction of sucrose. So we calculate the moles based upon the mass of each one. And the mole fraction of sucrose is 0.3131. So I know that was a lot of legwork to get one little piddly answer right. Let's see. A plant cell has a natural concentration of 0.25 molal. You put it in aqueous solution with a freezing point of minus 0.246. Will the cell explode, shrivel, or do nothing? So here, we're actually introducing the idea of osmotic pressure before we actually talk about it. What you want to do is know what is the molal concentration inside the cell and outside the cell. If they're equal, nothing happens, right? It's isotonic. But if the concentration is greater than 0.25 outside the cell, it'll draw water out of the cell and the cell will shrivel. It'll crenulate. But if the outside concentration is lower than the inside, the water will move into the cell and it'll explode. So that's where we're headed. We have to calculate what is the concentration of that aqueous solution outside the cell. Well, if its freezing point is minus 0.246, the delta T is 0.246. So the delta T then would be 0.246, and that's equal to molality times K. Well, let's see, K for freezing point was 1.86. Okay. So we can calculate the molality here just by dividing 0.246 by 1.86. Right?
To go backwards, but what was the boiling point? Just so I have right, so you got 1.86 and then what was the other number?
Oh, 0.512, I think.
All right, I just wanted to raise that, sorry.
Yeah, 0.512.
Oh, thanks.
Okay, so if we solve for the molality of that solution outside the cell is 0.246 divided by 1.86. You got it? 1323 mol. So that's outside the cell, correct? That means that there's more water outside the cell than there is inside the cell. And it's going to move into the cell and it should explode. Okay. Oh, there's the calculation. All right. So we're correct up to that point. There we go. Water will move into the cell and the cell will explode. Okay. Now for osmotic pressure. I think that was that the last one? Freezing point depression, boiling point elevation. Oh, vapor pressure. We already covered that one. And so this is the last one, osmotic pressure. Osmotic pressure formula. Osmotic pressure is given this symbol, pi, just like the math equation for a circle. And that's equal to molarity times the gas constant times the temperature. Okay. So if R is, if we need pressure, then what do we have to use for R? We have to use the one with atmospheres in it. Right? 0.08206 liter atmospheres per mole K. So the temperature has to be in K. And this one is molarity. Excuse me. Which is moles per liter. So this is, excuse me, moles per liter. So moles in the numerator, moles in the denominator, they cancel. Denominator, numerator, they cancel. K cancels, and we're left with atmospheres. So that means osmotic pressure is going to be in terms of atmospheres. That's the unit of pressure here. Now, if we wanted a different unit of pressure, we'd have to use a different value for R. But we're not. We're gonna keep it simple.
So R is always that.
For this equation, yes.
Oh,
And for our gas laws, whenever we had R for the gas laws, PV equals nRT, that was the one we used. Now, when we got to places where we were calculating energy, joules, we had to use that other one, 8.4125, I think. Joules per mole K. Okay, so why does osmotic pressure work? Well, a practical way of measuring it is to put the concentrated solution in this bulb with a membrane on the bottom of it and submerge it in pure solvent. If you do that, which way is anything going to move? If that membrane is semi-permeable, semi-permeable means it will only pass water or gas. For our purposes, water is enough. Only water will go through there. Nothing else will pass. So what you've got is a membrane here. You've got a solution here, and you've got a pure solvent here. So at the surface on that membrane, you've got, oh no, I got it backwards. I'm sorry. This is the solution inside the bulb. And this is the solvent. There we go. So think of it in terms of impacts, kinetic molecular theory against that membrane. And the solvent, the solution is made of the solvent and the solute can't cross the membrane, but the solvent can. Okay, so the solvent from both sides is impacting that membrane, trying to pass through it. Right? So which one's going to have a higher rate of crossing the membrane? The one with more impacts. The solvent, the pure solvent is going to have then on this side because you have solute molecules in the way here and impeding the movement of solvent molecules across that membrane. So we need to establish equilibrium. You need an equal rate going both directions. So until you do that, solvent's going to continue to move across the membrane into the bulb faster than it moves out. Okay? All right. So eventually, this solution rises up to a certain level. And now you've got the influence of pressure. So if you got this added pressure here, right, it's the liquid levels here and here. And it used to be here, but now it's up there. So you got a difference here of some pressure based upon the height of that column. So that pressure is contributing to more frequent impacts of the solvent against the membrane. Okay, and when that happens, at some point, that pressure gives you enough impacts so that the rate of crossing the membrane one way is the same crossing the other way. You have an equilibrium. And that pressure is characteristic of the concentration of the solution. So as the solution is increased in concentration, you need more and more pressure to establish that equilibrium. That's osmotic pressure. This is another way to establish it. The osmotic pressure in this U tube is the difference between the two heights. Right, and this equation may also need modification to account for dissociation. So we also have that Van Hoff factor there too. Okay. Let's see. How many more slides do I have? I haven't been keeping track. Okay, I'll try not to take too much time. I'm gonna leave that there because I think we're gonna need it to solve this problem. All right, we've got 33.4 milligrams of a compound. And actually solve it by reading it backwards. Calculate the molar mass of the compound. So we know, what do we need to calculate the molar mass? We need the mass of the compound and the number of moles. Mass per mole. So what do we have? We got the mass, 33.4. The mass equals 33.4 milligrams. How many grams is that?
40.34 or 0.334. Yeah.
Well, you got to move. This is going to get, the unit's going to get bigger, so the number has to get smaller. By how much? Milli is 1,000th, right? So we move it 3 places. Right? Okay. So now we got the mass. We need to find the mole. And we're also told that when we dissolve this compound in 10 milliliters of water at 25 degrees, the solution has an osmotic pressure of 558 torr. So we're given this value, but it's not in units of atmospheres. Right? We need 558 torr divided by 760 torr per atmosphere. That'll give us atmospheres. Okay. We're going to assume this is 1, so we'll throw that out. This is going to be our unknown, molarity. R is going to be 0.08206. I'm going to leave the units out for now. Temperature has to be in Kelvin. Yep. So 25, simply because this is liter atmospheres per mole K. So that has to be in K. Okay. So we can find out what the molar concentration is of this solution. Here's my calculator. Here we go. So I need this value, 558 divided by 760. And that's going to be 0.7342 atmospheres. But I want to take that value and divide it by this one and then divide it by that one, right? Because they're coming over here. And there'll be more decimal places than that. Let me change my display. There we go. This is going to be molarity equals 0.03024 molar. Now, let me see if that's right. I have a sneaking suspicion. I know that's right. 0.7342. Is anybody else calculating this one at the same time? Yeah, I get it the second time. That same number? You need to do these calculations along with me. Yeah. Otherwise, I could put anything up there and you'd have to believe me. But if you do the calculations, then you can call my hand on mistakes. Okay, this is molality, which means what? Moles per liter. So how many liters of solution do we have? Well, we have to assume, since the milligrams of the solute are so small, that we still have 10 milliliters. Right? So how many liters is 10 milliliters? We're going to go bigger, so the number has to get smaller by 1,000, correct? .01 liters times that number. And that's 0.0003. And that's moles. So now we can put it into this formula. I did my calculations correctly. Mass is 0.0334 grams per 0.0003 moles. And let's see. And I get 111 grams per mole. That's the calculation of molarity. Actually, I'm a little off on that, aren't I? Oh. Did I use the wrong value? I did. Oh, 558. That's the wrong calculation. Right? 588 is what I put in there. Right? So that's going to be I got to do one of two things. I've either got to change this over here or I've got to change the conditions back here to make it work. I think it'd be easier to change this one to 588. But be that as it may, we're in the right neighborhood. I calculated 111 with the correct value. And with the modified value, we got 106 grams per mole.
So back up real quick. You do the 0.734, and then you multiply it by the
No, divide
divide. So
Right.
you do that divided by this times,
by that and by that.
because I was having issues.
Yeah, I mean, that's algebra. Right? If it's multiplied on this side, it's divided on this side. If you move it from that side to this side, it goes into the denominator. Right?
So I got a question real fast.
Okay.
So the Kelvin or the 273, where do we get that from?
That's the case.
Last
So it's
semester.
always that.
Yeah,
Okay. I
that's how
just
you
wondered-
convert centigrade to Kelvin.
Okay.
273 plus centigrade is Kelvin.
Okay.
Your book might add some decimal places on it. 273.14 or 15. I always just round it off to 3. Okay. This is an interesting problem, but I'm not going to spend a whole lot of time on it. I'll just give you a little background. Everybody got this one? When I was a kid, I thought about things that I guess most kids didn't. But when I learned about the sequoia trees in California, and in science class, I said, okay, we knew that water could, if you put a tube into a bucket of water and you pull a vacuum on it, you couldn't get it any higher than 33 feet. That was it. Because the difference between no pressure in the top and atmospheric pressure on the other side would raise the water 33 feet. That's it. Wouldn't go any higher. So I said, okay, how do you get water to the tops of those trees? I mean, they're 200, 300 feet tall. You know? So one proposed theory was that it wasn't a push, it was a pull. So the tree starts out small, so there's no problem. Water can get to the top of that little tree. And as it grows, you know what the stomates are in the leaves and the needles? Stomates open and close to control water movement in and out of, and gas movement in and out of the leaves. So as it opens up, it's evaporating water out of those leaves. And as it evaporates the water, it tends to form the concave, but the water tension pulls it back. Right? So each time it loses, the water tension pulls it back. And when you have lots and lots and lots of little concaves that are pulling, maybe that's enough to pull the water up the tree. Well, to make a long story short, experiments proved that didn't work. That's not what's happening. So the other option that fits in with our discussion of osmotic pressure is what kind of pressure is being exerted in the xylem, right? If you know your plant anatomy, xylem is the part of the tree, the tubes in the tree that send solutions up toward the top, and the phloem goes from the leaves with nutrients down. Right? So the xylem in the roots are exposed to solutions around their roots And what we want to know is the difference in concentration outside the root cell of the xylem and inside the root cell of the xylem, is that concentration difference big enough to provide osmotic pressure that will drive water to the top of that tree? So if the concentration inside the cells of the xylem is very, very high, then you're going to get movement of water into those cells and into the xylem that way. So, and with these very tiny electrodes, they can go in and measure that pressure. And the pressure they found was 20 atmospheres. That's a lot of pressure, osmotic pressure, 20 atmospheres in the roots of those trees. So is that enough to drive water to the top of a 300-foot tall tree? Well, it's simple dimensional analysis from here on out. Right? How tall is that tree? Right, 300 feet, and we convert it to millimeters. Right? Why do we convert it to millimeters? What's the measure of atmospheric pressure in millimeters of mercury? 760, right? So we're headed toward millimeters of mercury by comparison of millimeters of solution. So that's how tall the tree is in millimeters. Then if we say atmospheres and convert atmospheres to millimeters of mercury, that would be 20 times 760, right? The first part of that bottom equation. But we want to convert it to millimeters of water, or roughly millimeters of the sap. Okay, so this is a rough estimate. Well, we need density. So millimeters, 13.56 millimeters of water equals 1 millimeter of mercury. That's the difference in density between mercury and water. So what we're finding is with 20 atmospheres, you can go 2 times 10 to the 5th millimeters tall. Well, you only need to go 1 times 10 to the 5th, right? 9 times 10 to the 4th, rounded off, 1 times 10 to the 5th. So you've got twice as much height as you need. We could go 600 feet with a tree if we wanted to. I don't know, maybe in prehistoric times or way, way, way back, maybe trees were growing bigger than that. But the ones we have now, we got plenty of pressure to drive that water to the top. Okay. What's a colloid? We talked about earlier, and actually last semester, you can have heterogeneous mixtures. Right? We know what that means. The distribution of particles in a heterogeneous mixture is not uniform. Excuse me, not uniform. You know, like mixing, I don't know, sand in water. Right. And homogeneous, we've been discussing that one the whole day. Homogeneous is the same thing as a solution. Uniform concentration throughout. There's a place in the middle. Now, solutions are characterized by the solute being distributed uniformly amongst the molecules of the solvent in such a way that they just occupy those empty spaces that we created. But we can have the solution, we can have a suspension, like heterogeneous, we could have a suspension. Heterogeneous mixtures, typically the suspended medium drops out of solution under the influence of gravity. Right? And it's dependent upon particle size. So the particle sizes of the suspended medium are large enough so that they drop out of the mixture under the influence of gravity. But if you make those particles small enough, then the kinetic energy of the dispersing medium that we would normally term as a solvent. The dispersing medium has enough kinetic energy that when they impact those dispersed particles, they can keep them suspended indefinitely. And when that happens, you get a colloid. Colloid is not a solution. Those particles are just small enough that the kinetic energy will keep them suspended. And we have various examples of colloids, right? Probably one that you are very familiar with is Jello. Now, Jello is kind of funny because you got dissolved sugar in there, which is a solution, but you've also got proteins, the gelatin proteins that are not soluble in the water, but they're small enough so that they can be suspended. And that, besides that, they're long chains and they tend to entangle with one another, and that helps keep them suspended too. There are other examples of colloids, right? And here we have in this table, and this came straight out of your textbook. A fog is a colloid of a liquid dispersed in a gas. So have you ever walked through a very, very, very thick fog? Like, you can feel very tiny, tiny droplets on your skin, but they're so small that they stay suspended. It's like a cloud on the ground is what it is. Those are called aerosols. A fog, an aerosol spray. If you have a solid suspended in air, like somebody's campfires or burn piles going, it produces that small particle size smoke. Now, some of those are large enough that they're going to settle out. You can see the ashes coming up. But some of them are small enough that they stay airborne. And those are also called aerosols. Whipped cream is a gas suspended in a liquid. So is soap suds. Gas suspended in a liquid. A liquid in a liquid is something like milk or mayonnaise. Now, the way milk gets suspended, things suspended in milk, the problem component in milk is fat. Have you ever scraped cream off the top of raw milk? Yeah. It will naturally separate from the milk. Unless, and of course, if you want to make butter, you just take that, churn it. But if you want it to stay suspended, you have to reduce the particle size of the fat globules. So you can either put them in a mixer with a very fast spinning blade, right? That'll do it. But the way the commercial dairies do it is they take that milk and under high pressure, they force it through a stainless steel mesh, a sieve. And the only thing that can get through it is either the liquid components or the fat if it's small enough. So it rips those fat globules apart into smaller particles, and once they get through, they're homogenized, and they'll stay suspended indefinitely. That's a liquid in a liquid. That's called an emulsion. The other way to do it is to put an emulsifying agent in there that bridges the gap between the two, but that's a little too complicated right now. If you have a solid dispersed in a liquid, we call that a sol. You know, I misspoke earlier. No, I didn't. Gelatin. Gelatin is a sol. So your Jello is a sol. You don't want to know where the gelatin comes from. Does anybody know? Yeah. It's a byproduct of the slaughter. They take cows' hooves and bones and boil them. The protein they get out of it goes into your Jello. Marshmallows, gases suspended in a solid. Right? Or polystyrene foam, same. I think those ceramic bricks that surround the space shuttle or the Elon Musk's Starship, those heat tiles that they put on the outside, those are very small gas particles suspended in that solid. That's what makes them good insulators. Let's see, a liquid suspended in a solid, like butter or cheese. Solid emulsion. Let's see, the gas in a solid is a solid foam. The liquid in a solid is a solid emulsion. And a solid in a solid is a solid sol. A ruby glass is like that. So the first laser that was ever invented was based upon a solid crystal of ruby, man-made crystal of ruby. And it was a colloid, a solid in a solid. So how do we tell the difference between a solution and a colloid? Right? If you don't know how it's made, there's a really easy way to do it. If you have your solution / colloid here in this container, and it's a beaker, so you can see through it. Then if you shine a light, like got your flashlight here, and you shine that beam, then you can see it on this other side over here. Whether it's a colloid or a solution, either way. But if your eyeball is out here, and I'm going to have to go down here to do that. If your eyeball is out here and it's a solution, you won't see anything. You will not see the beam traveling through the solution because there are no particles to for the beam to bounce off of and meet your eyes. Right? It's all they're all in there, all equal players, and there's no reflection off the particles. But if it's a colloid, you've got small particles in there suspended, and they will give you a trace. You can see the light beam in there, right? You can see it. That's called the Tyndall effect. We're going to use the Tyndall effect in one of our labs. It's the complex ion, lab number 5. We're going to use the Tyndall effect. When we titrate a solution that has silver in it, we're going to titrate it with a chloride salt and precipitate it out. But it's in competition with another reaction that wants to keep it in solution. So we titrate it to the point where we produce the silver chloride in the colloid, small particles colloid, and that's our equivalence point. But it's hard to detect. So we dim the lights and we'll take a flashlight. One person shines it through the reaction mixture and moves it around so we can see the beam. And when you can see the beam and it doesn't go away with mixing, then you've reached your endpoint using the Tyndall effect.
So with the Tyndall effect, you can see it from any angle. Is that what?
Mm-hmm.
Okay, and if it's not, you cannot see it.
If it's a solution,
Yeah.
then you won't see it, no matter where you are.
Okay.
The only way you can see it is if you're directly opposite. Then you can see the beam across the mixture. But if you're looking at it from the side or from above, you won't see the beam in a solution.
Okay.
Yeah. Only in a colloid. What do we mean by coagulation? Coagulation is a general term that describes the destruction of the colloid. And when we mean destruction, that means the suspended medium is no longer suspended, right? It drops out. The best example of that is when you fry an egg. Egg's got the yolk and it's got the white. And let's focus on the white part of the egg. It's a colloid of mostly proteins suspended in water. But when you heat it, those proteins change their shape. And now they're predominantly they contract into little balls. And that makes them very dense. So they would drop out of solution. But unless you go in there to eat them first. So coagulation is the destruction of that colloid some way. Heat does it. Sometimes you can add an electrolyte, like a salt. We call it salting out. Those are the two main types of destruction of a colloid. We're not going to do an experiment with that. It'd be interesting if we could. But that's it for chapter 11. And then when we come back on, let's see, Monday's the holiday, right? Tuesday's not. Okay, so we'll be here on Tuesday. We will discuss, oh, they're not out here. We'll take the review document and go through a discussion. And if you have looked at those review problems and you find any that are giving you trouble, can't figure out why you're getting the wrong answer, then bring those to class and we'll do those first. And then I have the some of those questions highlighted, so I can go through those. Fill in the time. We won't have any dead air. We'll do your problems and then I'll start talking. And then let's see, Tuesday, and then I guess Thursday is the exam. Yes, and the lab. So we'll do the exam, and 2 hours should be enough time. Right. Finish that.
How many questions we usually?
I'll have to look. Let's see, assuming I use this version. Actually, I've got points. If they're 1 point each. Yeah, they vary in points. So 67 points is not 67 questions, it's fewer than that. And then they're bonus. And you can try the bonus or you not try the bonus. It's okay. Just try to do what you can. If calculations are involved, show me your calculations. So that with the bonus, you have to work for it. And there's always the possibility that we'll go through a review document and work problems. And then when I put problems like that on the test, I'll change the parameters. So you need to know how to work the problem, not how to memorize the answer. Okay.